So let's look at the relationship between atmospheric pressure and altitude. Which of these four lines would best represent that relationship? Well, the green line says that as altitude increases, the pressure stays the same. That's not a good choice. The black line says that at any given altitude, the pressure is a little, and then it's more, and then it's a lot. That's not a good choice either, because we know that the atmospheric pressure changes with altitude. And so, of these two remaining lines, which one best would represent the relationship? As the altitude increases, the pressure decreases. So I think we're going to have to go here with the red line. However, is this relationship linear? And the answer is, it is not linear. In other words, while the graph generally goes down from left to right, does it tend to swoop down more and then level off as the altitude increases, or does it drop off only gradually and then all of a sudden the pressure drops substantially? Well, it turns out that this top graph best represents the relationship between pressure and altitude in the atmosphere. Fluid pressure increases with depth because the fluid at a given depth must support the weight of the fluid above it. We just talked about the atmosphere. The atmospheric pressure closer to the surface is higher than the atmospheric pressure at a high altitude because the air at the surface has to hold up the air above it. So it's got to be at a higher pressure in order to do that. And of course, this is true with liquids as well. For gases in the atmosphere, the pressure is greatest at Earth's surface. We've talked that the pressure decreases with increasing altitude, but it's not linear. And the reason it's not linear is because gases can be compressed. So when the gas near the surface is subjected to a higher pressure, it also compresses that gas, makes it more dense. This is not the case, as we'll see, generally, with liquids. For liquids, the pressure-depth relationship is linear, because liquids are incompressible. That is, the density, rho, is essentially constant. If we were to draw a graph that has the surface, okay, up here at the top, and increasing depth as we go down, what happens to the pressure as we go deeper in the water? Well, if you've ever been in a swimming pool, you know that your ears will tell you the answer. The deeper you go, the greater the pressure. And in liquids, this line is linear. That's not the case for the atmosphere, but for liquids, that line is linear, which is very convenient and will help us when we get to calculations. Let's determine the pressure on the bottom surface of each of these tanks of water. These are both filled with water. The tank on the left is 1 meter on each side. The tank on the right is 1 meter wide by 1 meter deep by 2 meters long. Now, pressure is force divided by area. So the force, in this case, is going to be the weight of this water, which is, weight is mass times the acceleration due to gravity. This harkens back to earlier physics lessons, mass times gravity. Well, the mass of 1 cubic meter of water having a density of 1,000 kilograms per cubic meter, that would mean that the mass of this water is 1,000 grams times 9.81 meters per second squared, 9810 newtons. The cross-sectional area of the bottom of this tank is 1 square meter. So the pressure at the bottom of this tank is 9810 pascals, newtons per square meter. This tank here, we have 2 cubic meters of water. So the weight of that water would be 2,000 kilograms times 9.81, which will give you a force, a weight of 19,620 newtons. Well, the cross-sectional area of the bottom of this tank is 1 meter by 2 meters, which is 2 square meters. So force divided by area, and you get the same pressure. So the key point here is that the pressure at equal depths in the same liquid is everywhere the same. It wouldn't matter what shape the container was. It could be a real skinny container, like a very, very tall grad cylinder. 1 meter below the surface of water. That's the pressure, 9810 pascals. Let's imagine we have this boot, and we fill it with water. Of the points that are labeled, which has or have the lowest pressure, and which has or have the highest? Well, clearly, point A is going to have the lowest pressure, because the depth above the surface is only that far. And pressure depends on depth. What about points B and C? Point B will obviously have a higher pressure than point A, and point C is at the same depth as point B. The fact that it's in the toe instead of back here at the heel makes absolutely no difference. The depth of B and C is the same, therefore B and C are tied for the highest pressure. Let's summarize. The atmospheric pressure decreases with increasing altitude, but not linearly. The pressure in liquids increases linearly with increasing depth. And thirdly, the pressure in a given liquid depends on the depth of the point of interest. Of note, the size and shape of the container have no effect on the pressure.